today and tomorrow, who is Michele Doro, a good friend coming from the University of Padova, member of CTAO, the Magic Collaboration, SWGO, an expert in Cherenkov telescopes, dark matter and fundamental physics done with these instruments. And these are exactly the three topics that he's going to talk about, starting today now with an introduction of the technique behind some of the science that we are talking about here, which is the imaging atmospheric Cherenkov technique. So, Michele, thank you very much.
Thank you, Ulysses, for the invitation and the presentation. I hope you can hear me. It's nice to see you here, so many. So, it's late in the afternoon, it's the fourth lecture, but still we had some topics to cover. I have prepared more slides than I will have time to share for you, even with the specific information so that you can check it after. Because I think you are all PhDs. Is there any postdoc? No. Few, okay? So all very young. And I decided to add a little bit to the original title, which was just focusing on imaging atmospheric Cherenkov telescopes to put, yeah, I forgot. Sure. To put some perspective, which I think is good for you and this community because of things that we will see, okay? So I hope I will make it on time. So that's me. I was already introduced. I'm an associate professor of experimental particle physics at the University of Padova. There is my email there already because I invite you to bother me at any time during this conference or in the next days if you have curiosities and if you don't find answer with your local tutor. Because the science that I will present, the instruments are really open for you to take profit of it. So if you need any just help, just write me and I will try to answer. So I was born, if you want, working with MAGIC telescope during my PhD and master thesis. I will talk about these telescopes later. And then now I'm happily or badly working for additional experiments, including CTA, sorry for the old logo, SWGO, which will be a very important instrument for South America, and Trinity, which is a neutrino telescopes. Again, if you have curiosities on this instrument for later, just tell me. Okay, so the program is this focus on gamma ray instrument, not only IACTs, focus on IACTs. And at the end, I put some question exercises for you to get deeper. I will not talk to them, but you can check them on the slides. And if you want to try to make those exercises to see if you have understood or what I said. So I think you saw this morning how it's a particular field, that of gamma ray astronomy, because with one messenger, which is the gamma ray, you can really do a lot of science, probably too much science for us that are trying to do. I don't want to go into all details. We have, you had, and you will have in this some more focus in this school. For example, from Elisabetta on gamma ray burst, from Gustavo Romero in general, for very high energy galactic sources, and this overview by Felix. So we have extragalactic science, we have galactic science, we have general topics in physics, and all these can be done with our telescope. So it's challenging to be able to grasp the whole field. That's why I'm trying to give you some advices. What's not written here is the topic of my next two talks, which will be tomorrow morning. Actually, there will be a slight change of schedule. I will be the first speaker of tomorrow morning, okay? And I will talk about especially dark matter and some other fundamental physics topics that can be done with gamma rays. Okay, so, well, this slide I can skip. I think you understood that whenever we use gamma rays, which is something around this part here, we are actually seeing sources that emit throughout the entire multi-wavelength spectrum. This is, for example, an active galactic nucleus, and you see that it's emitting the black line, follow the black line from radio to optical, X-ray, and then up to gamma rays, okay? And this is a bump that is aimed to explain the neutrino emission, okay? So whenever we are doing gamma ray astronomy, our instruments are really embedded into, they are looking into objects that are emitting in all the wavelengths, which is not always in astronomy, okay? So we are in the region of multi-wavelength, but also multi-messenger, as we heard this morning and this afternoon. Both from outside the galaxies, but even inside the galaxies. This is the pulsar wind nebula. You see that is emitting from radio, again, to gamma rays. Okay, so whatever data that we put must be put into the context. And it's important for you to, for the PhD and for after, okay, if you focus on gamma rays, also to have a general idea on what are the instruments in the other bands in order to be able to understand the spectrum, okay? So we enter, this was already said, into gamma ray astronomy. This is an amazing years for you and for us, because from one target we have gamma rays, neutrino, cosmic rays, gravitational waves, as we heard, which all together makes multi-messenger astronomy, which is one of the latest science born in astronomy, at least. Okay, so we cannot cover the entire multi-wavelength spectrum from radio instruments, okay, microwave telescopes, to the visible, etc. We will focus a little bit more on this part. And you see that whatever is gamma ray is something above roughly 1 MeV, which you should know as number. I will go back why this number here. We will have first satellite-borne experiment, and then ground-based experiment, like MESS, HEGIC, Veritas, and CTAO, which is the focus of this talk, plus HAWK and LASSO, which will be presented elsewhere, okay? Again, it's important for you to be familiar roughly with all of these scenarios because our science is multi-wavelength basically all the time. And the other point, which maybe you have studied at school or you need to know a little bit, is that whenever we talk about gamma rays, we actually are studying the field of cosmic rays because which is this nice, extremely nice spectrum. These are the cosmic rays hitting the Earth that goes along several orders of magnitude in energy, and this is the flux, okay? And you see this is the proton, for example, spectrum. And it's incredible that there is this linearity from 1 particle per meter square per second down to 1 particle per kilometer square per year, okay? So there is this continuity of protons hitting the Earth. And I mean, to have gamma rays, at the end of the day, we need them. We cannot generate normally gamma rays out of nothing. The way to generate gamma rays, as you have studied probably, is through inverse Compton of lower energy photons onto accelerated charged particle, for example, electrons. So you need an accelerated electron to have a gamma ray. Or you need to have, for example, a proton, which then further decays into or interact and generate photons, okay? So gamma rays, whenever you have gamma rays, you always need to think we have charged particle there. So there is a bunch of ways. These were 2 that I showed you before. I don't want to go too much into the detail, but you see that these are the way in which you can have accelerated cosmic rays and gamma rays in the universe. They can be connected to leptons or hadrons in these 2 rows, and they can be connected in columns with interaction with magnetic fields, radiation fields, and particle fields, okay? So proton-proton collision, for example, or synchrotron. It's a complex plot, which I don't have time. This is not the topic of my lecture, but you know there is this very, very useful book, which is called High Energy Astrophysics by, oops, I put the wrong one. I should have put the long hair one, sorry. But I will change it. It's also good, this one, okay? So we have gamma rays that are related in a multi-wavelength context and with cosmic rays physics. Now we want to, to understand how to have a gamma ray instrument, okay? So I don't know how much you have done, but if I ask you how to detect a gamma ray, okay, you need to think how to do it. So you have to go back to your books and remember that actually you cannot reflect gamma rays, okay? You cannot reflect, it's an important topic, no? Because normally telescopes, they are made so that you focus a lot of radiation and photons to a point. And this can be done from radio to X-rays, but in gamma rays you cannot do that, okay? They really interact too strongly with the matter. So you go again, or you remember, you check how gamma rays interact with matter, and you know that this is a cross-section, okay, in function of the photon energy, and we are here, no, in the gamma ray part. And this is an example that I took for lead, but it's the similar shape with every material. You see that at lower energies you have the photoelectric effect, and then you start to have the Compton effect, which dominates around here. But at the end, after 1 MeV is twice the mass of the electron, you start to have the most probable interaction is pair production, okay? So at the end, if you want to detect gamma rays, you start always with a pair production experiment or a Compton experiment. Okay, we'll see this how is declined in several cases. I don't want to make a physics course. The Compton effect, you know, is this scattering. Okay, so you have an initial photon which transfer energy to an electron, and then a lower energy photons up to a certain angle. I just put this slide because I will use this for an experiment in few slides from now. But if we focus on, so at the end, you can use Compton, you need some dense material, and then you need to detect the electron, for example, here, which is visible, okay? So if this is your original gamma rays, you may, for example, use the Compton scattering to and detect your electron. But if we focus on the pair production, which is what we will use in most of our experiment, pair production is when you have the interaction between two photons now, okay? For example, a lower energy photon and a higher energy photon, which makes two particles with the opposite charge, okay? The two photons, one can be a lower energy gamma rays, a gamma ray. The second photon can be either the electric field of the atom or a free photon somewhere. No, you know the pair production effect. And then out of this you generate electron pairs, muon pairs, whatever helps you, whatever respect the symmetries and kinetic rules at that time. Okay, so as we said already, about 1 MeV electron pairs can be created, and so you start to have two electrons. Again, you need some dense material and the capability of detecting electron. Now, by this, no, we learned that we have to use the pair production if we want to access those energy, but how to design an instrument, okay? We saw, and I will show you that there are many gamma ray instruments, how to generally design it. It depends a little bit, no? It depends, first of all, what are your science goals, okay? Which drives you, the general design of your instrument. And then you have to know the general details of the instrument that you want to build. You have to follow the technological advancement at the time. You have to add your fantasy in the instrument, because you can start to have, I will show you some slides, new ideas. Also, the software is not the latest part, because out of the same instrument, if you do a better software, you have better data, okay? And Claudio knows that we also need funds to build the telescope. Okay, so just now, like this, we are in the gamma ray part. I want to show you a general overview of the gamma ray experiments. There are many lines here, so what is this plot? This is energy range, okay, in MeV. So a line here tells that this instrument, for example, CTA, is sensitive from this energy up to this energy, okay? And this is the sensitivity, which is the minimum flux that this detector can see, okay? It's called sensitivity. So the minimum, the higher the plot, the worse the experiment, if you want. The lower, the better, because it can detect a smaller flux. So this is a picture of many instruments. doing gamma ray astronomy, and you see these, some are on the past, the one on the top, Comtel and Negrete. I will not talk about those. These are the present ones, Fermilat, you heard, Magic, Hawk, High Score, and Lasso, okay? So they are lower now, and in the future you have maybe GEMX, GEMUSO, eAstrogam, and CTA, okay? So it's what you see here is not only this top-down effect, which you improve with the generation of telescope, but also you see that these are sensitivity curves. There is not one instrument that can cover a very large energy range, okay? So every of these instruments, Fermilat is very good here, okay? Magic is very good here, Lasso is very good here and here, okay? This you need to understand the field. There is a specific reason for this. I let you during the slides to try to reason why it's like that. Why it's so small, and also it's not that easy, but you see that all these curves are shaped like a U, okay, or a V. There is a question at the end. I'd like you to think why it's exactly a U or a W shape, okay. There is a reason for this, and if you answer that, I think you can learn something. So this is the sensitivity, the general thing that say the power of the instrument, like that. But it's not only sensitivity that matters if you want to build an experiment. One very important part is what we call energy resolution, okay? So the capability to discriminate between photons of similar energies, okay? Close energy. I want to know if it's 100 GeV or 105 GeV. I need to have a detector that has enough energy resolution. If you see here, for example, it's a comparison that I made on 4 instruments. I will discuss them later, but this is Fermilat. You see 5% here, and then decreases up to 25%. CTAO here, okay, between 10 and 15%, but on larger energy. So here is better than Fermi. And Lasso is here, okay? There is a lot of reason why these lines are there. But as long as you try to approach gamma ray astronomy, you have to, I suggest you to try to understand why we have this specific curve. And if you read the paper and if you do this, you will quickly learn about it. Why it's important, energy resolution, okay? Not because we are that much picky, but for example, we want to see, this is the Crab Nebula, we are here, no? We want to see the cutoff, the end spectrum here. The end tell us a lot about the energetics at the source, okay? If we have a bad energy resolution here, the cutoff can move from here to here, no? Depending on the way we call the energy. So a good energy resolution is, allows you, for example, to be able to make a nice cutoff, which in turn tell you the energetics at the source. So energy resolution. The other factor is the angular resolution, which is instead now the capability to tell the direction of 2 events, okay? And you see that in general, for example, this is for CTA, it's around 0.05 degree, 1 arc minute, okay? Which you say, well, is it good or bad? Well, we'll see, for example. Why it's important, the morphology, okay? If I have this source here, okay, this is the image of my instrument, and this is the point, what is called the point spread function, so roughly this area here. I want to know if this is extended or not. Is this extended from here? Well, no, yes, because it's slightly larger than the PSF of the instrument. To know, well, for galactic targets, to know the morphology is extremely relevant because you have all the information there, and it's you see really how the object is shaped, not just a blob, okay? So to do this, also Ulysses knows very well this portal. He helped build it. There is a portal which I recommend you, which is called firmamento.newad.niu.edu, which we helped build. And you have, when you input a source, for example, this name here, okay? This is a blazar. You input the source, it automatically gets the coordinates. And the first thing that you have is this sky map, okay? So the sky map contains, it's around the source, contains circles. What are these circles? These are the angular resolution that I told you before. So the uncertainty on the position of the telescope. So this is, for example, the name is not written there, but I know. This is Fermi-Lat. Sorry, there is a wrong name, okay? Fermi-Lat, this roughly 0.1 degrees, very big, okay? In gamma rays. If you check the angular resolution, for example, of X-ray, okay, it's much better. And if you check the red inside, this is radio, it's even better. So it's very different. What is the problem with gamma rays, okay? How many, well, this is maybe not very clear here, but within this gamma ray source, you can have a lot of radio or X-ray sources, okay? So it's important to have the smaller possible gamma angular resolution to be able to say, okay, this signal comes exactly from that source and not another one, okay? So there is a reason why the angular resolution of gamma rays is worse, and we will talk about this later, than other telescope, but also it's another thing to keep in mind, okay? The comparison between instruments. What we have now, also another important plot, and this will be probably the last one, is what we call the effective area, okay? The effective area is, you know, when you have a flux, if I want to compute a flux from a source, I have some number of events that I detected, okay? The number of events is the event in my detector, okay? How do I move from number of events to flux? Flux is something in function of the time, the observation time, and area, okay? And here I have to put an effective area, which is the acceptance, you say it's the geometrical area of the instrument times the acceptance. You don't care about the geometry of the instrument only, you need to know how good is your instrument to detect a source. So, say, the effective area is the geometrical area times an acceptance factor, which is the fraction of the number of events that you see reconstructed with respect to what you simulated in total. So this would be, I don't know, 10%, then 10% is something here. And you see that, for example, CTAO is super large, no? 10 to the 6 meters square, okay? And then it decreases, okay? It decreases here. Fermi-Lat is much, much lower, like 1 meter square. You say, aha, wow, then CTA is much, much better than Fermi-Lat. It depends on what you're looking at. And there is also a reason why these lines are like that. And it's important to know the effective area to compare instrument because they tell you how good they are in detecting the sources that you have. For example, okay, you say, look, if we compare the sensitivity, this is the same differential flux. This is energy, and you see this is CTA, and this is LAT, the Fermi telescope, okay? You see they look very similar, no, on the level of energy. But then look at the time. CTA does this in 100 hours, and Fermi does this in 10 years, okay? Wow, 10 years against 100 hours. CTA is much better. Well, it depends. Fermi-Lat, it's always there looking at the sky. CTA needs to point the telescope, as we will see. So, for example, the sensitivity is not interesting per se. There is what we call the sensitivity in function of the duration of the event. If the event is very short, like we heard about gamma ray bursts or gravitational waves, you don't care to observe for 10 years. Who cares? You need to observe for a few seconds, okay? Then CTA, the differential flux, the sensitivity is much better than Fermi-Lat, okay? So CTA will be able to detect very short bursts. And they more or less, why 10 years? Because it's more or less the time in which you can compare the two sensitivity. Okay, and finally, okay, you have your detector, you're looking at the sky, you have to ask yourself how big is your field of view, okay? It's not granted that every technique has the same field of view. Okay, if you have a telescope, normally you have a limited field of view in the sky, which is maybe something like this one. If you have multiple telescopes, you can displace them and maybe look at a larger sky. But we will see that if you have a satellite, instead your field of view is of the order of steradians instead of just square degrees, so much more, okay? And the last, really this is the last, so we said effective area, angular resolution, energy resolution, the field of view, but also the duty cycle, okay? We will see that even when we present LASSO, we don't have instruments with all the same duty cycle. For example, some instruments will only work at night, some will work 24 hours per day, some are outside the atmosphere, so they work all the time, okay? So the duty cycle is the fraction of the time during the day or during the year in which you can observe, which determines a lot the science that you can do, okay? I mean, for you about this is, now we are entering into a phase in which you will have access to a lot of data, much more than my generation, because we were using more experiment, and now you may have access to all the data about this gamma ray band in the future because they will be shared, okay? So it's important for you to understand what constitutes an instrument, not only then the figure of merit, but also you have to check if the data are available. I will tell you about that. With what delay with respect to the event, if you have instrument-related software that you can use, or general astrometric software that you can use, and if you can apply, okay, as a guest observer program, not really needing to be part of the instrument to observe this part. Okay, if you have questions, I told you there is a large community now growing in gamma rays. You can ask around. You can bother Ulysses or me or whatever people in this room, because you will have access to a lot of data. And you may bring ideas that I will show you that we don't have. You can bring proposals that we don't have. You're young, you have the time to develop things for the next 20 years in which gamma ray astronomy will reach probably its maximum. Okay, so concluding all of this, okay, we have a lot of features that make an ICE experiment, okay, and I will show you that there is not one instrument, one Swiss knife with many instruments there that can do everything, okay? We need to have multiple instruments, which complicates a little bit the thing. Okay, so questions for now? I'll take a breath and everything clear? You want to have more details, something that was not clear? Cannot be. Or clear, okay. Okay, then I'll take my water. Okay, so instruments overview. We will focus mostly on high energy detectors, so I will not go into X-ray and lower energy instruments, there is no time. But even here, our field, the field of gamma ray astronomy, it's kind of, we always look, say, even if you work in one instrument, you have always to look to the other instruments which are working in your field. So this is a sketch with increasing energy. Okay, you can sometimes have some lower energy gamma ray or cosmic ray detector mounted on balloons, which are regularly shipped into the atmosphere, especially from the northern region, like for example, Arctic, which makes very nice cosmic ray measurement rather than gamma ray measurement toward lower energies. Then we will see why, okay? We start to enter into the mega electron volt and giga electron volt gamma ray regime, and to observe this, we need to go into the space, okay? So we'll have instruments mounted on satellites. Then, if you increase the energy, okay, and you enter into the TeV regime, you have to move your telescope basically to the ground, and there are instruments called imaging atmospheric Cherenkov telescopes, which are the basic of this talk. I will talk more about this. a little bit about those. While if you go even to larger energy, these are not sufficient anymore, and you build this fancy instrument, which are called shower array detector, which I like them because they are water telescope. No, there is a light telescope, and these use really water to make telescopes. So it's a camera pointed at the sky. If you really want now not to gamma rays, but you want to detect the latest part of the higher energy part of the cosmic rays, you go into nice instrument in Argentina, like Auger, for example, to detect the cosmic rays. Okay, for time reason, I will basically focus on these two. Mostly also this part will be covered by some colleagues in the future. Okay, so if we see them, now before talking to them, we look at them all together. We look at the overall field. You see something like that. This is called the Kifune plot, okay? Which tells you the number of sources which were detected over the time, okay? It's interesting, no? If you are moving at the science, actually, you can build your Kifune plot. There is a GitHub page, so you can use this for your thesis and change it as much as you want. So, see X-ray, this is the yellow line, okay? There is some number of instruments. There is no need to look at that. But you see that the science started in the 60s, okay, with one source, Scorpius, and now in maybe 30 years, they have 10 to the 4, 10 to the 5 sources, okay? So hundreds of thousands of them, after many instruments. If you go to GeV, gamma rays, which is satellite-borne instrument, this started in the 70s, okay? And you see how the increase is lower, but you see how we pass from 1 to now something like this is, so Egret and then Fermi, which is the final generation, and you see it's about 10 to the 4, 10,000 sources, okay? Nice. The telescope that I will talk about, it's the last open window, okay? Started in the 90s with one target. It increased low, the first generation, the second generation. Now the third generation has magic veritas, has magic and veritas mostly. And we are here of the order of 300 sources in the sky. It doesn't say that there are 300 gamma ray emitters in the sky. There can be thousands, but we just observe only 300 of them. Why it's relevant for you? Because CTAO is so powerful, I will show you later, that it's an open to the public that we expect to have thousands of sources. So when you double the number, when you triple and multiply the number of sources, there is a lot of science that we don't know that it will be there. So for you, it's a very nice thing to try to understand how to make CTAO analysis. Okay, so this is our field, and I will focus mostly on this part here, okay? About the space experiment, I just want to tell you very quickly. I have 1 hour, no? 1 hour, okay. So, before Fermi, there is a some lower energy instrument in this window here, okay, below, this is the KV part, okay, in which we have an instrument, integral, this is the black line here, okay. There is another one that is now not working anymore, and this one is just proposed, okay. I don't know why this was never approved, because you see how much better it is from the previous generation of instrument, this Astrogam. And when you have to work into this regime, KV, you remember my first slides? You want to detect gamma rays around the KV. What is the interaction technique is the Compton one, okay? Compton and two-word pair production. So if you want to detect those, you need to have a Compton instrument, okay? So for this, you have to go into the space because the atmosphere absorbs them. And one of the most famous Compton instrument is Integral, which is this kind of telescope. And at the end, it's a stack of material, no? In which you have some dense material in which the inverse Compton must happen, okay? And then you want to detect the electron out of the inverse Compton that leave some energy into a calorimeter. Because the inverse Compton doesn't have a trajectory, everything is, you don't know the trajectory of the electron, okay? But it doesn't matter, because if you see one electron from this part here, multiple electrons, at the end you can reconstruct the direction, okay? I don't want to go into too much the detail of this. This is an old instrument, but I want to tell you a few things. So what you can do, okay, using the figure of merit and other things that you can learn, is to go into their page, and you will see all the things that we discussed about, okay? You can see the energy range, good. The detector area, fine. The spectral resolution is the energy resolution, and you can check it here. You can compare the field of view, the angle resolution, blah, 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 okay? I don't want to go now into the details of this, but I want you, if you have time after the conference and during the next years, have a look at this, because you can learn how instruments are by comparing this. On integral, there are two instruments, SPI and EBIS. I don't want to tell you much more. The angular resolution is not so good. So the galactic center, which should be one of the closest objects to us, is only very broadly defined, but still integral provided a lot of science, okay? Now I think it will be dismissed. In the future, pay attention to this new Astrogam instrument, this is the old version. This is an ICRC of this year document in which we still want to propose this new KV instrument, which is, you remember, sorry, I go back, here, okay? We know we can reach the sensitivity, and the previous ones were there. So this is very much interesting to have an instrument that is more than 200 times better than the previous one. Okay, so we have KV instrument, and why you say, I don't care, it's not my field. Yes, but if you know, sometimes I want to put this attention. This is Marco Cirelli, a friend of mine and colleagues. The Voyager 1 is an instrument that left the solar system, no? And the data are public. And you say, okay, who cares about that instrument anymore? But no, if you look at the data, if the data are there and you know how to use them, and you know the instrument, you can maybe put out a paper, which was that time a constraint on primordial black holes, in which there was no interest in the collaboration to do it. But you have the data, and you can make questions and have access to the data if you know the instrument, okay? So try to expand a little bit, and this is the last time I will tell you about this. During these years, what is the whole field of gamma ray astronomy, okay? Okay, more now into the GV. So we are here now. We will focus on the latest instrument, okay, the best one, which is the Fermi-LAT. Now, these are different names because these are different catalogs of sources from Fermi-LAT. Now we are in the 4th Fermi catalog of sources with 8,000 sources. We are here, okay, GV, MEV, so GV is here. And this is where Fermi is trying to be mostly sensitive, okay? You will see that here there is, nobody is better than Fermi in this energy range here, okay? So now we have pair production, and you see that it's very similar to the previous instrument. What you need to have to make pair production is an absorber material and then a tracking system, because you have the gamma rays from the source that you want to have, which interacts with the matter, okay? And this is the pair production. The red arrows are 2 electrons, okay? So in principle, it's quite simple, and this is technology that was developed at accelerators, okay? So it's very well known. These are particle physicists working in space that's built this very successful instrument called Fermi, which received the Rossi Prize for the science that he made in the past years. So again, some sketch, okay? You have the initial gamma rays. After some interaction length, you have to have an interaction with the material there, which I think is germanium, I'm not sure. Okay, pair production, and then you also have a secondary event, which is Bremsstrahlung here, okay, which goes there. At the end, this is your event, okay? If you have a satellite, you have these 2 lines plus the energy deposited here. And out of this, you have to say, okay, look at the angle. Now, this was the direction, okay? This gives you the angular resolution. The amount of energy here gives you the energy, etc., etc. So this is your basically the idea for an event. And you have to also make, I will come back to this, to screen it from charged particles in the atmosphere. This is how it looks like. You heard before about LAT, which is this top part, and GBM by Elisabetta. GBM is this instrument below here. Okay, again, the figure of merit, just for you to have a look later, if you want, about these parameters here. And you can check yourself, all the information there, okay, in the Fermi satellite. Now, you see that the image is much better than integral, no, of the galactic center. This is Fermi, okay, quite detailed of the galactic center, and this will be a projection from ground-based telescope. So, much better angular resolution, much better view of the galactic center. We have thousands of sources. Now we said 8,000, okay? You see they are sparse over the sky. And there are about 8,000. I want to tell you that the gray dots are the ones that were previously done and assigned by Fermi. And there is this work now, which we are about to finalize with Marcella. Marcella? Yeah, she's there. So if you are curious, just talk to her. In which by, say, rechecking their data, Fermi-LAT data, we could add something like 400 new stars in the sky, okay? So we are not Fermi members, we just probably defined a cleverer way to associate target, and we found 400 new sources. So it's a very populated sky there, okay? There will be, there is a poster by Marcella on this conference there. Okay, we had Fermi, very successful one. There is a less lucky one, instrument called Agile, which was delayed by some political reason. It's a kind of a small Fermi, but again, you have, so a very similar instrument, a very similar concept. Now it's not working anymore. I think it was exploded in the atmosphere, but the data are public, okay? Who knows, if you, for your project of thesis, you may be able to use Agile data there. So if you're curious, you can just go there and look at them, okay? No need to ask and to pay for anything. Fermi also has the most advanced, I think, data analysis tool, okay? You need to analyze those data. You don't want to reconstruct the data from the detector. You want to have data that you can use. And Fermi has, so far, I think, the best set of tools to analyze those data. It's freely public. And Ranier, there, yeah, sorry, we'll talk about that, no, I guess, with FermiPy, no? Right, exactly. So, no need to work on the experiment, but if you want to analyze the data, you better know what the instrument is. Okay, so very quickly on the space. Now, more time on our ground-based instrument. I will focus on these ones. So what is the story here? So again, this part here of the spectrum now. We are in the part now higher energy in which you see Fermi-LAT is toward the end of its sensitivity. And now there is a bunch of lines because we have several instruments, Veritas, Magic, and HESS. What is HESS? I don't know. And in the future, we will have CTA here with some friends working nicely here at a larger energy. But in this energy range, you see from here to basically here, so from 1 GeV, 10 GeV to 20 TeV, CTA, again, there will be the best instrument, okay? So I think everybody wants to work with the best instruments in that energy range. So what is the problem with doing astronomy in the gamma ray astronomy in the Earth? No, you say, okay, a gamma ray out of space interacts with the atmosphere, which has some density, no? So how am I able to see a gamma rays from the ground? Well, happily we have the atmosphere because we would be burned by gamma ray flux. It's not that big from astrophysical sources, but still, if you go to outer space, you know, the astronauts, they have this gold layer to protect themselves from radiation from the space. Here we have the atmosphere, but the technique is the same, no? There is some dense material, so at the end, if it's gamma ray above the MEV, you always have pair production, okay? So what's nice is that, okay, I'm happy, I have a gamma ray interacting with some atoms, I have 2 electrons, and then do I lose the electron or not? This is the point, because this happens, it depends on the direction a little bit, but you can say that this happened roughly at about 20 to 10 kilometer height, roughly, an idea. Okay, so you have 2 electrons at 20 kilometers made by a gamma ray entering the atmosphere. Now, these 2 electrons, okay, if you think, if this is a gamma ray of, for example, 1 let's say 1 TeV, okay? This one is 1 TeV, okay? This is a photon from the electromagnetic field of an atom, which has basically no energy, okay, compared to that one. What would be the energy of the 2 electrons? Roughly, no? Roughly, it's this one divided by 2, okay? So 1 TeV, 500 GeV, okay? For each of the electrons. 500 GeV for the electron is pretty large energy, okay? And if you check here on the way electrons lose energy, okay, again in matter, this is where you will have Bremsstrahlung, okay, from electrons. So these 2 guys here, they will make Bremsstrahlung radiation. What is Bremsstrahlung? You know, no? Is, for example, by simple deflection, you have an acceleration of the electron, centripetal in this case, which gives you additional radiation by breaking, which is called Bremsstrahlung, which again are gamma rays, okay? So it doesn't end after the first pair production. Okay? So we have the primary gamma rays, this one, coming from outside the atmosphere, which generates 2 electrons, well, an electron and a positron. And on these 2, you have the Bremsstrahlung. So the positron stays the positron, but also make a Bremsstrahlung gamma, and also here. Now the Bremsstrahlung gamma, this one is a secondary gamma, it's not the first one. But this is roughly, no, you have a 500 GeV electrons that makes a gamma ray, and you can assume that roughly it's also the energy split in 2. So the energy at this level would be 250 GeV, which is still a lot of energy. This is still a gamma ray, and this is still a very energetic electron, okay? So you see how this process creates, one primary gamma ray creates a shower of particles in the atmosphere, okay? Or a cascade of particles. If you want to model it, there are several kind of simplistic model. One of the first and most famous one is the Eitler model, in which doesn't care too much about these little differences in height, and you say, yes, I have 1 layer, first layer, second layer, third layer, fourth layer, okay? So this is the primary gamma, pair production, electrons and photons, and if you count like that, you see that the initial energy, the number of, at each step, the energy is divided by 2 to the n, okay? And then what you need to learn is that the maximum energy, the maximum development, this process cannot go indefinitely when it ends, okay? We go back to pair production, it ends when the electrons has not enough energy to make Bremsstrahlung anymore, and it just do ionization, okay? So ionization is low energy, it's very frequent, and then you lose the shower. So this process ends when the energy of the electrons is the critical energy in the atmosphere, which is roughly 85 MeV. So you follow this step, and when you count the energy that is 85 MeV, okay, your shower ends. This is relevant for what we want to observe. So I anticipate something that I will tell you. So we have this, okay, many steps here of the shower. The number of the number of steps is the initial energy divided by 2 to the n, and you have a certain maximum extension, okay, which is again this 10 kilometer. At here you have the energy of the electrons are 85 MeV, roughly. You have ionization, you lose the particle, okay? So the shower dies here. So it never goes below 10, roughly 10 kilometers, okay? This is why actually fly, you know, the airplanes, they fly at 10 kilometers. And that's why pregnant women, they don't, when they are pregnant, they don't work anymore. They have to really go down to ground level because the level of radiation that they have is larger than they would have at the ground. So you don't wait until the last months, okay? So the shower is there. One of the first that studied this 100 years ago was Bruno Rossi, which is the founder of my institute in Padova. Is this guy here, which basically also selected the name shower, docce in Italian. And I just put it there, and I just don't read the slide, but for the Brazilian, Bruno Rossi was a very friend of Brazil, and he helped back then. He came visiting Brazil, so you can read about this later. He was a colleague of Lattes and others here, so he was part of the beginning of the cosmic ray astronomy, which we know that in South America is really one science that you started, you contributed so much. So you can read a little more about Bruno Rossi there. So the simple sketch that I showed you about the shower, this Eitler model, is actually too simple, no? If you will really look at the proton shower, this is not a gamma ray shower. It's not that regular, it's kind of a mess. But what happens is you have a proton, it's similar to gamma rays, and this is the particles that are actually found in the shower, okay? So it's a little more complex than by a simple scheme. Everybody of us working in gamma ray astronomy sooner or later start working with the program that actually does this, tell you exactly how this is the event. You can do it analytically up to a certain extent, but we do now on simulation, and the software is called Corsica, Cosmic Ray Shower, I don't remember the name, and for Karlsruhe, right? Which we use, and you see, for example, the atmospheric shower from a photon, okay, nice. A proton, different, hydron particle enter into the atmosphere, and the muon shower, okay? All this is simulated, and we do a lot of simulating Corsica shower and analyzing them. If you want to build a ground-based detector, you need to do that, and you need to know what is Corsica. So, we have our shower in the atmosphere. This is a sketch, and we know that at a certain point it dies here, okay? Because here is when the energy of the electron, I repeat myself, is critical for the ionization to be more efficient. Okay, so this is the height. Now, if we turn it, the height of the atmosphere is here now. Is the radiation length, so 0 is the top of the atmosphere, 5, 10, 15 radiation length. Ground level is roughly, the atmosphere is roughly 30 radiation length. And now here is the number of electrons that are made into the shower, okay? It's a complex plot, but let's take this. I want to observe 300 GeV photons, primary photons of 300 GeV. This plot tells me that the maximum number of electrons happens around here, 5 to 7, okay? and then it goes, it decreases, then the shower dies off here, okay? But if I have, for example, I don't know, 120 TeV, or even here, photons, the maximum of the shower happens much lower in the atmosphere. So this will be important for SWGO, which we will see tomorrow. This, the height of this, what is this? Is the height of the maximum here. This depends on the energy. If the shower is more, the gamma ray is more energetic, the shower will develop until further down into the atmosphere. Okay? But at the end, if it's 300 GeV, you don't see it, okay, at sea level. We don't have those particles there. So how can we detect these gamma rays if the shower dies off? Luckily, there is a second event that happens, okay? So I'm more in physics. So our telescope is below where the shower, the particles are. How can we see this event? There is a phenomenon called Cherenkov radiation, which I assume you have studied at school, which is happening. You know, this is two situations. You have a charged particle passing through a medium. The particle will be the electrons of the shower, okay? If it's slow enough, this will create dipoles in the atmosphere, which slowly, in a certain sense, goes back to the zero charge, so no dipole solution here. So there is no dipole. There is, at the passage, the atmosphere is made as a dipole, okay? Now, if the velocity of the electron is larger than the speed of light, c, divided by n, which is the index of refraction in the atmosphere, what happens is that there is still the same phenomenon, this dipole creation, but the dephasing of the dipole is now coherent, okay? Is now coherent, so they dephase in a way that a coherent wave front can be generated. I don't need the details here because you know it's the same effect as the sonic boom, okay? When the velocity of the airplane is larger than the velocity of the sound waves behind the airplanes, they get in phase, and that's why to your ear they are in phase and you hear the boom, okay? Which is all sounds emitting from different times but arriving to you at the same time coherently. It's exactly the same, and it's called for light Cherenkov radiation, which was discovered in Russia several decades ago, okay? Why we like that? Well, I don't need this now. Because now we have the coherent picture. We have our incoming gamma rays. We saw the shower of particles. We show that the shower happens at about 10 kilometers, but then it dies off here, okay? So we are lost unless we build instruments like particle detectors, like SWGO, for example, or LASSO, which will be spoken about. But then if we don't want to go there and we want to stay at warmer places and nicer places in the world, like the La Palma Island, where I work, to 1-3 kilometers, you don't care about the particle. You can observe indirectly twice the Cherenkov light emitted by the atmosphere at the passage of the electrons, and now this Cherenkov light is UV blue, okay? And we know, because we see the sky, that the atmosphere is transparent to blue light, okay? So this blue light, UV blue light, can out propagate from 10 kilometers pretty much undisturbed until the ground. So this is what is called Cherenkov cone, and then you put your telescopes there, and you see, you reconstruct first the shower, and then the incoming gamma rays. This is the general idea. Okay? Is this clear? Okay? Good. So I will not focus on this technique, but only on this part. Now, I left something behind a little bit. It's time to speak about this now. This is the electromagnetic shower from a gamma rays, which we discussed so far. But we know, okay, that basically every gamma that we have from a source, we have 10,000 proton For each gamma, we have 1,000 proton hitting the atmosphere. What protons? These are the cosmic rays that I told you before, okay? So we are here now, TV. We have a lot of 1 every meter square or tens of meters square per second, a lot of protons. What is the shower? What happens to a proton when it enters the atmosphere? It's pretty much the same, a little more complex. Proton, okay? Again, interaction with atmospheric nuclei. Now you don't have pair production. What you do with protons, you have quarks, and then you do pions, okay? Now, you do pions normally roughly with the same probability over the 2 charged and the neutral pion. The neutral pion makes decays into gamma-gamma, no? You know that? And now this gamma has the same energy of this gamma here. So out of this gamma, there will be an electromagnetic shower as this one, okay? So it's much more complex now, no? Well, if you follow a charged proton, pion, well, I don't know what I said before. Pion, you have muons and neutrino at the end, okay? Now, the neutrinos will cross the Earth. The muons will reach down to level. You know that we have a lot of muons here. They come from this shower. Now, we have 1,000 of those for our signal that we want to look at this. It's complex. How do we do, okay? How do we find our gamma every 1,000 background event? Luckily, you see that this complicacy helps us because at the ground, the gamma ray shower is very regular, so it's kind of a very regular and central thing. The proton is a mess, okay? So if you build an instrument that understands what mess is, like this, you can reject a lot of this. And our rejection power depends, this is a general number, depends on the energy, but it's more than 99%. We can get rid very quickly of the proton event. Okay, so I think I will make it on time. So this is the signal that we want to look at. Now, it's not as easy. I will try to look at this to understand you how we see it at the telescope level. But you can imagine you have, if you look at the sky when it's raining, okay? If you look at the sky when it's raining, the rain is parallel, no? It goes down by gravity. But you don't see with 2 eyes, or even with 1 eye, you don't see it unless the one that hits your eye, the one that is slightly off axis, make a straight line in that direction. So you see lines like that, no? Kind of, they are not parallel as you look at them. You know they are parallel, but you don't see them parallel. It's kind of the same happening here. So you have Cherenkov light emitted from here, all the path, no? Here, and then here, and then here. And yeah, I should have told you that. The Cherenkov angle here, you see that it increases. Now, this is smaller, larger, and larger. This depends on the density in the atmosphere. Now, so this is photon. The photon from the top of the shower enter here and is reflected there. And this is this point here, purple, okay? From the center of the shower is reflected more into the center there, and then from the green part to the outer part. So the image of the shower of photons, it's an ellipse. Maybe I do a picture here. What you see, you have the Cherenkov cone, okay? You have your telescope here, and what you're looking at, it's Cherenkov photons that are going to the ground, which is, this is if you cut the ellipse with a plane, if you cut this cone with a plane, you have an ellipse, okay? This is roughly the ellipse that you see here, okay? Which gives you the image, if you want, is the indirect image of the electromagnetic shower. If you look at one of these in a real event, it's an ellipse, you see it here. It's this one, and it's pointing toward the center, okay? Because it's like the rain. You see all the lines, they converge to a point, which is where it's up for you, okay? Why we make multiple telescopes? Because Well, the image is here. Where is exactly the center? No, here or here or here. If you put more telescopes, you have the two similar events, and now the precision from the direction where they come from is much better defined. So that's why we always put multiple telescopes. So this image is our event, and what you do is you study this image. So that's why they are called imaging atmospheric Cherenkov telescope, because this is the image. Ranier will tell you a lot about how to do this, I think. In a video, so that I also took some water, this is what happens from CTAO. You have the shower happening in the atmosphere. These are only particles for now. This is the Cherenkov light. That is the only thing that propagates. The electrons are dead in the atmosphere, and the light travels, okay, hits the mirrors of the telescope, goes into the camera, and make our image there, okay? The light is blue, I told you, and the duration, okay, you don't imagine minutes, the duration of the event is few nanoseconds, okay? So you need to have the telescope that detects nanosecond. Okay, so to make this true, you have to build a telescope like that. First of all, this is magic, no? What you need to have? A large mirror, okay? This is a standard mirror. Why large, okay? Why do you need, this is 17 meter. Why it's large? It's not because there is a sacred number, but because you have the density of photon at ground is not that large. So now we cannot focus the primary gamma rays. It's impossible to focus gamma rays, but we can focus the Cherenkov photons, which are blue, okay? So we build a large mirror which converge all the Cherenkov photons into one point, okay? So you will see that basically all of them are 12, always smaller than around 10 meters. You have a mirror, okay? And you have, on a structure which goes into, that can rotate the telescope. You have a camera onto which the mirror is done, and then the electronics and the signal transport. So basically the main idea of the structure, okay? The structure, well, 70 meters, it's a big telescope, but it's not the, the usually large telescope that we know. It's much simpler, okay? This old telescope, for example, for MAGIC weighs 60 tons, which is very, very little, okay? Why do we want to have lightweight mirror structure? This depends. At the beginning I told you, you have to think how you want to build your detector, okay? What did we learn tomorrow with Elisabetta? We have events in the sky that happens very quick. In a matter of seconds, you'd like to be there, okay? You have a small field of view, okay? So you cannot see the whole sky in a sense. But this is the one topic that may give you the Nobel Prize. So your telescope must be possibly moving very fast to that position, okay? If you build a very bulky telescope, fine, you have a very bulky structure, but then it takes a lot of minutes. Normally, all telescopes in the world are very bulky. It takes minutes to go into the position. MAGIC and all the other telescopes, they can take 20 seconds to move 60 tons from each direction to another, okay? So lightweight structure driven by science changes a lot the way you want to build your instrument. Okay, so lightweight, and then must be elastic, not to change the direction. What do you want for mirrors? Okay, well, 70 meter, it's a large area, and it's blue light. So you say, well, okay, it's an optical mirror. Optical mirror for optical telescope are extremely expensive, really, really, really expensive. We don't care about this, so a good mirror means very, very precise shape, okay? So sphere, and also very, very good micro roughness, what is called, both things. we care about the shape, but not a lot about the micro roughness compared to optical telescope. Why? Because the two events that we see are different. An optical telescope is looking at a very point-like source far away, okay, outside the atmosphere. They want to make morphology. What are we looking at? Not a point-like source. Our source is the shower, which is extended. Who cares about the sub-arcsecond angular resolution? Our event is per se larger, okay? So you want to have instead, okay, so you need average quality mirror. What you want to have is mirror that survive. There is no dome, okay, on this telescope, so they want to survive outside. Optical mirrors do not survive without the dome. Why we don't have the dome? Because we need to point so fast that it's impossible to make a dome rotate that fast. And again, here is a lot of technology, okay, to do this. You want to build a photon sensor here. What do you need? What is your event? We argue that the event is an ellipse, okay, in a focal plane, and then you have to make the image of the ellipse. If you want to make an image, you have to at least pixelize the image, okay, and its surroundings. So the first thing, you need to have a pixelized camera, okay? So we need to have a pixelized camera. The second thing that I told you is the duration of the event, okay? The duration of the event is 1 nanosecond, okay, or few nanoseconds. Then you cannot use, I mean, even this one is a pixelized camera, no? But it's very slow, okay? You cannot use a CMOS to do this. You need to have pixelized but very quick photosensors, and then you use fast photosensor like photomultipliers, usually, or silicon PM, okay, which has transit time of nanoseconds. So both things, multi-pixel and fast photosensor. We are talking about 2,000 pixels, roughly, and fast photosensors. And then for the DAC, you want to design a data acquisition system. What is the problem? Is that I want to measure something that lasts, say, 5 nanoseconds, okay? So this event in my camera will last for 5 nanoseconds. So if I check the signal on this pixel here, there will be nothing, and then something, and then nothing, and this is 5 nanoseconds, okay? In order to be able to see this, my electronics must be faster than this, no? To shape this. So my electronics, I have to make my electronics, which is, again, something like the gigahertz, okay? Or fraction of it. So I want to have gigahertz electronic running on 2,000 pixels, running on multiple telescopes, okay? And each one is a signal. If you count by standard electronics, well, it depends a little bit on the dynamic range, but this is a lot of data, no? To do it. And then you say, okay, well, when is the next event? So I have my event, I start recording, it lasts 5 nanoseconds. When is my next event, okay? The rate, roughly the rate of gamma ray when you look at them is 1 hertz. But including the background, our telescope goes on 100 hertz, roughly. So the next event will happen after 1/100th of a second. And it lasts 5 nanoseconds. You don't want to record all of this. It's no signal, okay? So you need to you have to think, this is the signal that you want to sample, so you have to make the electronics, how? Well, quick, here, and also you must be able to make an electronics that stays always listening to an event, but not registering the event. Only if there is a trigger, then it starts to record, okay? And then, when there is a trigger, you need to read all the pixels and write them on the disk. This part is pretty challenging. It's one of the fast electronic things that are done in particle physics. But again, you need to be able to do this. You don't do this with the optical telescope normally, okay? You don't care about this. Okay, so these are the general idea of this instrument, at least in my opinion. And then I leave for you a little more details on each of these, okay? On the structure that I just told you, but these are left for offline check. This is me because I was responsible for the mirrors of the telescope. This is the inauguration of the second one. There is complexity in mirrors, but I think it's no interest of this school, but every part of an instrument, I like technology, it's really amazing. To have an instrument successful, you need to do a lot of things. This is an example of the image that we have, okay? These are nanoseconds, and this is how the event look like for us. These are different cameras, okay? And we never said that. We have a lot of IACTs, and you see they have different shape, different granularity, but roughly they are all the same. So I can tell you that these are silicon PM based, this one too. These are photomultipliers, but more or less it's always the same. So multi-pixel plus fast photoelectrons. And this is the magic camera when it's open from the back, okay? From each detector you have an optical cable. It's a pretty complex device. Okay, I'm going toward the end in my next 10 minutes. So we said we have our gamma event. How would it appear? Like an ellipse here, plus all the other pixels lit by background light. And you clean the image and you have your cleaned event. And this is, when you study this, you have the primary gamma rays feature. We have gamma rays, we have background event like hadrons, which are more irregular, and night sky background. It's the light of the night sky. This I told you already. You make a study on the image, and here it's, as with every image, there is a lot of work now with neural networks to study the image, because at the end for us it's like a cat for neural network. So we classify images by the shape. For example, it's an ellipse, so the width of the major axis, the minor axis, the orientation, the distance toward the center. You clean the image. You classify this with a neural network to say to a computer, is this likely to be, more likely to be a gamma ray or a hadron event, okay? And there is a lot of work increasing over 20 years and even in the future to understand whether each event is a signal or a background event. We do this, for example, by classifier called hadroness. You see that we assign to each event a parameter called hadroness, which is, if it's 0.9, means that the event is very likely to be a proton. If it's 0.1, not very likely to be a proton. I use this because it's also for my tomorrow lecture there. At the end, okay, we want to see if we detected the source by this. We do this by counting. So this is theta. It's important, so I spend a second here. Theta, we have an event and we say, well, it should come from this direction, okay? If it's a gamma ray, it must come from where we point the telescope. If it's an hadron, it comes from everywhere in the sky. So we count the distance from where we say the event comes from and the center of the camera. This is called theta. Okay, and this is a plot with theta. Okay, it's square, it doesn't matter. You see that we count events in the signal and background. All events that we expect from the source should come from very close to the center of the camera. But we always have events that are background events that survive our selection. So we count the detection by counting in the area center of the camera, okay? We have an area here. This corresponds to this line here. And we count here, this is the sky, okay? We count here how many gamma event and background event we have, okay? Irreducible background. And then if this is significantly larger than the background, we have a detection of a source. It's pretty much indirect. So you see here that we have few background, almost zero, and a lot of signal. This is a strong detection of a source. Okay? But most of the time we have cases in which we have a lot of background and maybe a few excesses. Okay? All our fields, all Fermi, Gamma, Magic, they don't do counting experiment, they do signal over background. So you always have a certain number of background counts with some uncertainty, and you want to look at an excess of events over your background, which is the basic statistical analysis that we do, okay? All of this, for you, if you want to study more, is, I think, very, very nicely summarized into this paper by a colleague of us, Statistical Tools for Gamma Ray for Imaging Telescope. If you want to really study the statistics behind it, this is really good. And normally you learn it by the tutor, but then the tutor doesn't have time, so it's better go looking into a nice paper which tells you all the detail about this. Okay, I'm toward the end. What do we do at the end? Okay, we have gamma rays. Our main results are what we call spectral energy distribution, okay? So we want to generate in a plot which is energy and spectrum. These are all the wavelengths, okay? So radio, optical, X-ray, Fermi, we are here. We want to put points in the higher energy band here. And this is what is called spectral energy distribution. So after you have reproduced all your data, you are able to say, okay, I have observed that many photons at that energy, okay? It's complex, It takes a lot of steps until you can not only say the number, but give the accuracy and the precision of that number. So spectral energy distribution and light curve, okay? Light curve means that, as you heard before, the gamma ray sky, for reasons that will be clear during the school, are not stable. You don't have a gamma ray emitter which stays constant in time. Most of them, they fluctuate. The light curve is how many photons you get over the time. It's really the fundamental tool to make studying gamma ray astronomy. And so we produce both spectral energy distribution and light curve. And to tell you how complex the field is, and to close with the beginning, this is for one source. Markarian is the most strong blazer happening to us. And you see, this is in Fermi, actually, but you see how it changes over time. Sometimes it goes 10 times as strong as it was in the baseline, okay? And the spectrum changes in function of the time. If you go to this server here, Markarian Data Center, also by a colleague of us, you put the name of the source and you get automatically this light curve. And you learn how these guys, they are varying. You want to see one wavelength, but if you look this into the multi-wavelength context, this is how it becomes scary, okay? This is the plot that we publish now. So this is time, okay? And this is, where is magic? There, okay? You see that this is for another Markarian source. You see that each source is flaring here. And you want to look how these variations are seen in all the other wavelengths to learn how the source is behaving. And of course, I don't want to go into this detail. There will be talks about it, but it's very, very complex to do this on an accurate level on all the wavelengths. But if you want to do gamma ray astronomy, you have to pass by this part here. You are lucky, luckier than our generation, because now we have, and I'm closing, Gamma Pi, which is a software that allows you to analyze all gamma ray data, including Fermi. So Fermi, mass, edges. So with one open source package, you are able to analyze all the data. which is freely available. If you want to work on this, you need to learn gamma pi. There are a lot of tutorials there, so you can learn it. And even there is a standardized gamma ray data format, so all data that we will produce will have the same. So at a certain point, in a few years from now, you just don't care about the instrument. You take them, you analyze every data with the same format as it was one, which is super fine because you just want the value there, okay? So all these, just a few slides to conclude for you. To make instrument, you need to be creative. When there was first the idea, you know, this idea came into the 50s, okay? And out of this, just by somebody say, well, maybe there is Cherenkov light, let's try to look at it, okay? The first physicist that did that took a dust bin, okay? Put one photomultiplier and look at the sky like that, okay? It didn't work. It didn't work. Then I said, well, okay, too optimistic, okay? Then I'll try to put more dustbin. And also it didn't work, but they observed proton signal. They didn't observe gamma rays, okay? So it was the 60s, you remember maybe from the first plot that the first source in our field was detected in the 90s. So it took 30 years of technological development from the dustbin now to have much nicer telescope like MAGIC, okay? There are two. There is not only MAGIC. This is the current IACTs in the world now. MAGIC is in La Palma. You see here, two 70-meter telescope started in 2004. The second one is in Arizona. It's called Veritas. 4 telescopes of 12 meter, okay, here, sorry. And then HES in Namibia, 4 telescopes of 12 meter plus one huge one of 28 meters. These are the IACTs doing science now. And let's say working separately as collaboration. But now the future is this, and I really am closing. We are here with MAGIC SM Veritas. Now CTAO is coming. I will spend 1 word on this. We have LASSO and we will have HAWK, okay? We have HAWK, sorry, and there will be SWGO, okay? So when you will be finishing your PhD, you will start to have a lot of data for the best instrument really in our field. Not all of this will be open, but SWGO, HAWK, CTAO will share the data. So you will have a bunch of data to be able to use that. So CTAO is an ACT with the conjunction of HES, MAGIC, and Veritas, collaboration all together. We have now 3 nice telescopes. One is 23 meters, one is 12, and one is 4 meters diameter. It will become, at a certain point, a reality, okay? In the past, I was putting 202 something, then 203 something, then I decided to put 20XX because we hope, okay? And this will be, so I spoke about 2, 3, 4 telescopes. CTA will be 19 telescope in the north, 60 or 70 telescope in the south, actually in Chile, so this continent, in Atacama. The north one will be in Canary Island. This will be really the maximum that we can achieve with this technique. Okay, it's a worldwide effort. Everybody's there, but you will have access to the data anyhow, even if your country or institute is not part of it. You see how things change. Now, this is MAGIC, and we did a lot of science with MAGIC and HES, okay? And then now we have an instrument which is, this is sensitivity curve, sorry, which is like that. So you see he goes to much lower energies, lower energy threshold, much higher energy reach, okay, up to here. And then the sensitivity goes down by a factor of 10. We have great expectation, okay? It's really, you pass from a Fiat Panda to a Ferrari, okay? All of this will make, okay, all this pass by the figure of merit, which I told you to study a little bit more, which helps you help us a lot. There is IACTs, there is a bright future anyhow with the other instrument, like all the fields of gamma ray astronomy. If you want to work like that, you need to know a little bit on all of them. And so to conclude, I think, and I think I make it on time, so we are investigating non-thermal phenomena in the universe happening at galactic and extragalactic scale. Means that our field is totally multi-wavelength and multi-messenger, okay? It's important to know this when you study this. You cannot just focus on your tiny little energy range. The energy coverage is granted through satellites and ground-based experiment, and there will soon be the best instrument in the world, SWIGO, CTAO, and other instruments sharing data, okay? So it's important for you, if you want to become gamma ray astronomer, to have a multi-wavelength and technical overview on all these instruments, okay, to be able to analyze the data. And all of this, if you want, and you have funds, there will be a CTAO schools which gives you a little more, much more details about these techniques, and it can be followed, I think, offline. Sorry, this is totally, well, this was the question for you to check, and I'm really finished now. Thank you very much. So, 5 more minutes.
Thank you, Michele. Questions?
Thank you, Michele, for the talk. I think I missed something in the slide 62 about the...
Yeah. How do I do it? 62. Yeah.
Yeah, that's it. Thank you. If you take like a water and Cherenkov detector, we have a refractive index of 1.3 more or less of the water. So the particle has to reach a velocity, a speed of 77% of the speed of light. But in this case, we are in the air, so the refractive index is around 1. So how can the particle reach a velocity higher than the velocity of light in the air? So
it does. The refraction index, I mean, I don't know exactly how to convince you. The refraction index to the 10 to the minus 6, okay?
yes.
1 plus 10 to the minus 6, but is still enough for the electron, you know, at those energy is GeV, hundreds of GeV electron is still enough to make a radiation. Actually, I have the threshold here. It's 20 MeV. I think I put in my slide. So the threshold, where was it? Here, okay? The minimum energy, if you count this, is 20 MeV, okay? So as long as your electron has energy larger than 20 MeV, you get Cherenkov light.
Okay.
I know, it's strange. The angle, what is the difference? The angle, it's 1 degree here, okay? For in atmosphere, if you have a tank, and then you have water, it's I think 40 degrees, something like that, okay? Yeah. So the Cherenkov light is then 40 degrees, okay? So it's because of that.
Thank you.
You're welcome.
Thank you, Michele. So I'll take advantage of the slides, and I had a question on slide 70. So you already went back, right?
Yes.
Yes, okay. So you mentioned that some of those cameras are made of photo multipliers. So I guess you measure photoelectrons of the signal.
Exactly.
But the ones made from silicon, what are the numbers on the y-axis? What are you measuring?
Y-axis, this number here.
Yes.
Here, I don't know, is the intensity in some units that I don't know, probably the number of integrated flash LDCs. Silicon PM, I think it's exactly the same, okay? There is not a different except from the technology part. But at the end, you have your electric signal summed over a silicon PM. So if you want the electronics after that is roughly the same. So it's photoelectrons for the silicon PM, but for the, for the photomultipliers, for the silicon PM is electrons, okay? And there are advantages and disadvantages. I don't know if you are familiar with that, but silicon PM are really cheap and good and small. They cost a little, so but they are small. So that's why still we have photomultiplier-based camera. But it's very likely that in the future everything will turn into, even for SWGO. But SWGO is different. But exactly. The problem with silicon PM is that they have maximum 1 centimeter times 1 centimeter, okay? If you do them too large, you have too much capacitance, so you cannot really reconstruct the charge. The camera is 2 meter wide, okay? 2 meter means you want to put 2000 pixels, means that your photomultiplier is roughly 1.5 inches, which is 4 or 5 centimeter. If you want to cover one camera with silicon PM, there is one camera actually like that, but it's millions of them. You have to sum them. There are more complications. But at the end, it's electron and photoelectron. It's really maybe a little more energy resolution, but it's comparable. Okay, you don't know it when you analyze the data.
Thank you.
You're welcome.
Okay, so this might be a silly question, but like for Hess and MAGIC, you showed the telescopes are of the same size. But for CTAO, I think there are 3 different sizes. Like, I'm guessing there is some advantage, but like what is the motive behind having 3 separate size telescopes?
Yes, this is due to, I don't know if I need the slide, but it's quickly answered. So 23, 12, and 4. This, it's a good question. Why that large? You want it large. What matters is the photon density at ground. Okay, you want to be large if the photon density is small. Okay, so that you collect more photons. When the photon density is small, for lower energy showers, well, here, no? Suppose that this is a high energy shower. A low energy shower would be like that, okay? So much less Cherenkov photons here, density. High energy, a lot of photons density. So to detect a low energy gamma rays, low energy, I mean maybe, I don't know, 30 GeV, you have little density of ground, and so you need to have it larger, 24, 25. High energy photons, you don't care because you have a lot of photons, so you don't need it that large. What you do is, okay, I don't do it large, but I put many of them, okay? And that's why, maybe there is a plot here. Yes, okay? We have 4 large. So the red one are the large telescopes, so 23 meters, and many other smaller telescopes, okay? So this is the reason of the size.
Thank you.
Other questions? Yes, Claudio.
Claudio.
I don't know if I know the answer, so I want to confirm.
Okay.
So basically, to get the signal from this, Cherenkov spot, you have actually 2 problems with these telescopes. One is that their field of view is rather small. It means that you have to look in the right position of the sky where the gamma is entering. And the second one is that the spotlight, the light cone, is also very restricted. So even if you're looking at the right direction, but this thing is pointing in another way from your telescope, you won't produce an image in the camera, right?
Well, no, wait. So we are here, okay? The source is here. If from what you said, the source is like that, this is pointing to Vega, probably, no? All the gamma rays that are coming to us from this object, they are either like that, it's that far away, if you want, these are parallel, okay? Here, okay? So it's never that tilted. If it's that tilted, it's pointing to another planet or another solar system, okay? Right? So now, all the gamma rays from this source are kind of almost parallel to us. We can detect these, but we can detect also this one, which is focusing the camera, okay? So this is the impact parameter. At the end, when we say 3-degree field of view, means that we detect all the signal coming to the Earth, if you want. Okay, when it's too off.
Okay, so the point is that if you have a source in the sky in that direction, that source emits gammas in all directions. So some of them will hit you, basically. That's the thing.
Yes and no. Yes, but most of the sources are have a direction. Gamma ray burst have a direction. AGN have a direction, okay? A principal direction, okay?
Yeah.
A radio galaxy, yes, emits, if you want, emits in all directions, but not with the same probability, with the same intensity. So yes, but yes. It also illuminates in other galaxies, yes. No, the disadvantage, the main disadvantage for gamma ray astronomy is the field of view. But on the other hand, these allow us to need very little time to have strong signal, okay? So it's totally, with respect to SWGO, it's totally synergetic. You don't, cannot pick one, in my opinion. Exactly.
Okay. Anyone else? So if not, let's thank Michele again.
Thank you.